The Earth is a three-dimensional geoid, which is essentially a sphere that bulges slightly at the equator. Because of this, a three-dimensional globe is the only geometrically perfect way to accurately represent the true shapes, sizes, and distances of our continents and oceans simultaneously. But globes carry obvious practical limitations. They are expensive to manufacture, highly inconvenient to pack for a journey, and entirely useless if you need to zoom in on the granular, local details of a single city block. For humans to efficiently travel, trade, and navigate, we needed a way to compress this massive amount of geographic information onto portable, two-dimensional surfaces. Flat maps solve the problem of portability. However, opting for this two-dimensional convenience demands a strict physical compromise with reality. To map the Earth, we rely on the graticule, the three-dimensional network of intersecting latitude and longitude lines that wraps around the planet to provide a coordinate system. The core physics problem is simple. You cannot force a continuous, closed, curved surface into a flat plane without breaking its structural integrity. When you attempt to force that flattening, the mathematics dictate that the surface must undergo physical trauma. The material has to be stretched, skewed, or torn apart. Because of this geometric trap, every single flat map you have ever looked at contains mathematical distortions. Cartographers manage this damage using map projections. These are mathematical formulas designed to systematically transfer that three-dimensional graticule onto a flat page. The process relies on developable surfaces. These are specific three-dimensional shapes that, unlike a sphere, can actually be unrolled and flattened into a two-dimensional plane without tearing. Mapmakers primarily use three specific shapes to catch these projections: the cylinder, the cone, and the flat plane. Choosing the shape is the critical first step. The geometry you project onto dictates exactly where your final map will be distorted. This process is governed by the rule of tangency, or the point of contact. At the exact coordinate where the two-dimensional surface physically touches the three-dimensional globe, the resulting map is perfectly accurate. The inverse is also true. The further away a region is from that physical point of contact, the more severely the mathematical formula must stretch the landmass to fill the page. To measure this exact stretching, cartographers created a diagnostic tool called Tissot's indicatrix. It places perfectly equal circles across the three-dimensional globe. This heart-shaped projection uses Tissot's indactrix. Near the center contact point, shapes remain round, but at the extreme edges, they violently warp into slanted ellipses. On this second dual circular projection, poles are stable, but circles heavily stretch at the outer equatorial edges. Distortion on a map is never a random error. It is a highly predictable, mathematically controlled side effect of the chosen projection. Because a geometrically perfect map is impossible, cartographers face an ultimate dilemma. They must choose between preserving accurate area, accurate shape, or accurate distances. You cannot have all three at once. This vintage map uses the Mercator projection. It preserves angles, known as rhomblines, so sailors could draw straight lines across the page to navigate oceans. But the mathematical cost is severe. The projection wildly exaggerates the physical size of landmasses toward the poles. Prioritizing one geographic truth, like oceanic navigation, forces a visual distortion that alters our psychological perception of the world's size and layout. Geographic information systems eventually automated the mapping process. Today, cartographers use massive computing power to compute highly complex minimum error projections. These modern algorithms use polynomial equations to spread the required distortion evenly across the globe. No single area is perfectly accurate, but nothing looks outrageously wrong either. Yet, despite incredible computing power and highly advanced algorithms, the geometric puzzle remains entirely unsolved. A perfect map simply does not exist. Every map is a deliberate, calculated compromise built to tell a specific story. To read a map accurately, you must first figure out what it chose to sacrifice.